Hi everyone. So this is a very brief intro to the concept of simple harmonic motion. Uh, this is going to be the very next topic that we're going to cover. For the most part, this entire unit should kind of almost be a recap of a lot of stuff that you learned in trig and earlier math. So what does it mean when something is in simple harmonic motion? Like what are we actually referring to? For the most part, simple harmonic motion refers to any scenario where an object or a system repeats its motion over and over again. So that's that's what we call simple harmonic motion when it goes back and forth or it goes around. There's a bunch of different examples. Pendulums are probably one of the most common examples because pendulums tend to go left and right, back and forth. A person going on a swinging on a swing set is a perfect example of simple harmonic motion. Its motion for the most part is consistent throughout. But other common examples that you'll see would be things like masses on a spring. So if you place a mass on a spring and let it oscillate back and forth, that would be considered simple harmonic motion. Having objects sitting in water waves or just water waves in general, bobbing up and down in that repetitive motion would be simple harmonic motion. Probably the most common thing that you may not think of though is the Earth orbiting around the sun, or even just the Earth rotating around its axis. That's another perfect example of simple harmonic motion because again, it repeats itself over and over and over again. So this is the idea of simple harmonic motion is repetition. For the most part, we're going to focus mainly on masses on springs, but everything that we say can be extrapolated and used to explain things like pendulums swinging, objects bobbing in the water, the Earth orbiting the sun. All these things can be described pretty much the same way as we talk about masses and springs. The only difference is some definitions or some equations may have to be shifted out because of different relationships. Now, for the first part in this first lesson, we're just going to focus on some terminology. Again, some of this should be recap either from trig when you learned it in math, or kind of what we learned in previous parts of this classes. We kind of use some of these terms here or there, but this is where they all kind of come together. So the first one is this idea of equilibrium position. So right off the bat, you could tell from the name that equilibrium position has something to do with the concept of equilibrium, that the forces are balanced. And basically, it's the point where it has two kind of scenarios. It's either the point where the object is in equilibrium, so all the forces are balanced, or it's the point where if there is energy in the system, so such as like it has excess kinetic energy, it may end up resulting in the object not being completely in equilibrium, in which case we would say that if the object had all that energy removed, it'd be where it would be in equilibrium. It seems a little bit weird, but there's two different scenarios. So if we take the object on a spring and have the object oscillate back and forth, there will be a point right at a certain section where the object will be in equilibrium, where the force caused by the spring and the force caused by a spring could be zero, or maybe it's balanced out by gravity depending on how it's oriented. So in that case, it would be the first definition, that it's the point where the object's in equilibrium. But pendulums, one thing that you should have remembered in the circular motion unit, when an object's moving in this pendulum form, this is technically circular motion because it's moving in a curved path. And when it's moving in a curved path, the object is always accelerating, which means that it is always experiencing some net force. It will never actually be technically in equilibrium. At the lowest point, there will be actually a tension force pulling up that's greater than the gravitational force pulling down. Again, it's a recap from circular motion. So in this case, this would be a scenario where we'd say, okay, well, if I got rid of all that energy in the system, all that kinetic energy that's keeping it from being in equilibrium, Where would it lay? Oh, it would lay right here, so that's my equilibrium point. That's where the object would be in equilibrium if I removed all the energy from the system. So even though technically as it swings, it is not in equilibrium at that point, we would still consider it the equilibrium position. All right. The next term is this idea of restoring force. So the whole point of simple harmonic motion is that there's a force that's causing it to return and repeat this motion. If you just drop an object onto a floor and it just falls down and hits the ground, that's not considered simple harmonic motion because there's no really restoring force acting on it. There's no force trying to bring it back to equilibrium. But for a mass on a spring, there is a force. It's the spring force. So when you have a mass, bobbing up and down on a spring, the spring itself is what's providing a force to bring it back to equilibrium. When the object elongates and pulls to the, like, let's say to the right, then the spring is going to pull it to the left. If it starts moving to the left, then the spring pushes it to the right. So there's always going to be a force kind of trying to bring it back to that equilibrium point. And that's what's causing it to repeat this motion over and over again, to basically oscillate. In the case of pendulums, it's a little bit more complicated. It's kind of like a weird combination of gravitational force and the tension force on the string. But the key thing about the restoring force is that this is not a separate force. This is not like if you were to draw an FBD, you would never write F restore or something. There's no equation for restoring force. It's just a term that we give it. We give these collection of forces. It's actually just like centripetal force. If you recall in the circular motion unit, again, that the centripetal force was the effective net force causing the object to go in a circle. So sometimes it could be equal to a tension force if it was a horizontal circle. Maybe it was equal to a component of the tension force. Maybe it was equivalent to the normal force, or maybe it was a combination of normal and gravity or tension and gravity. It's the same idea with the restoring force, that it's not a new separate force, but a combination of forces. Now, for the most part, we're going to, again, only focus on the spring aspect. And in the spring case, the restoring force would be considered the spring force. The reason I want to clarify this, though, is that you may see some questions because of the early focus on springs. You're going to see some questions that will use the term restoring force and spring force interchangeably. Because, again, for this case, they are the same thing. If you're talking about an object oscillating because of the spring, the restoring force is the spring force. But I want to clarify that technically the restoring force can be any force that's providing the harmonic motion, that's allowing it and keeping it in this repetitive motion. All right. So here's actually a perfect example of the mass on a spring. So again, as it gets pulled down, the spring elongates and starts pulling it back up. You can imagine that if you actually did pull the spring down, you would feel the spring wanting to pull it up. If you then took the spring and compressed it, you would feel the spring kind of wanting to push you down. So again, if you kind of think about playing around with the spring, you'll see how as you move in a certain direction, the spring will always want to pull in the opposite direction. And again, that's the idea of the restoring force, that if you're, in this case, below the equilibrium point, the spring force will restore you by pulling you up. If you're above this equilibrium point, the spring will try to restore you by pushing you down. Again, that's why it's called restoring force. Another term, again, this comes from math, but one of the other terms that we have is as a system oscillates, a lot of times we'll have what's called the amplitude, which is defined as the maximum displacement that the object is from the equilibrium point. For the most part, all these harmonic motions should be symmetric. So the positive amplitude and the negative amplitude are the same. So if it can go, the highest it goes is 2 meters above the equilibrium point, then the lowest it goes is 2 meters below the equilibrium point. So it should always be symmetric. Again, just like you should have learned in your trig classes with sine and cosine and stuff like that. Um, the one thing I want to the amplitude is measured in meters because it's the length. I do want to mention one thing again. Even though we're going to have our focus on springs, it doesn't mean it's the only one that we're going to look at. I'll go back to here. For a pendulum, it's a little bit hard to define, well, what would be the distance here? What would be the length? Would it be the straight line length from this point to this point? Is it this arc length? Is it the height? Is it the horizontal distance? Because there's such a weird scenario of what could the length be considered, and it also makes a lot of scenarios really mucky to consider it. Scientists actually just will consider, instead of like a physical length distance, will actually refer to the angular displacement that the object is. So like sometimes you might see like, oh, this was displaced with an amplitude of 20 degrees or something. And the idea would be that would be the maximum angle from where it started, and that it would go back and forth with a symmetric angle. So again, just want to throw that out there in case I don't mention it later on, just so that you kind of notice it. There's a few more terms that I have to go through. Another term is period. This is actually something we covered again in the circular motion unit when we started talking about a little bit about orbits. So the period of a harmonic motion, of anything that's going in harmonic motion, is the time it takes for it to make one full cycle. So the time for it to go from this point to the right and then back, that would be one full cycle. So it has to return to wherever it started, and it has to be doing the same thing. So for clarification, I'm going to try and delete. No, there we go. Let's say I want to start here. So like, let's say I want to pick this point as my starting point of the cycle. Well, if I just did it right to where it returns to that state, you'll notice that this isn't the full cycle, because in the scenario that I picked just now, I started here, but I was also picking the point where it was starting here going to the right. Well, even though it's back at that equilibrium point, it's moving in the opposite direction. So in this case, if I want a full cycle, it would have to go to the right, down, to the left, and then back. Again, it has to return back to the same state it was in. So it's not just the physical point it passed, but also making sure that it's going in that same direction it was originally. The term revolution, oscillations, and cycles, they're all for the most part interchangeable. You'll see them thrown around in various questions. Usually they get asked for different scenarios, like revolution tends to be used for objects moving in complete circles. Oscillations would be things that basically shift from side to side, side to side. And a cycle can sometimes be used for, I mean, cycle kind of flips with all these, but sometimes with like waves and sounds. Sometimes they will use that. Again, doesn't really matter. No one's gonna hurt you or take off points if the question says that that something did 15 oscillations and you said 15 cycles. Like no one cares. Now this should be a new term, frequency. Now again, you should have learned this in a math class, but this should be new in this class. So frequency is the number of times it oscillates every second. And the frequency is going to be measured in hertz. Few things to note. If you remember one thing that I mentioned about period, the reason it's given the symbol of t is because it's time. It's just a fancy time. So just keep that in mind. For frequency, it's given this like scripted f. You want to make sure that you try to keep it like that. Just because of the fact that You don't want to accidentally confuse it with force. Like, so even if you wrote your F like that, it might get a little bit confusing. You might accidentally confuse it with force. So giving it this like little curved top and bottom really kind of separates it from the force equation, especially since you're probably going to have to use both equations at once. You'll have some equations dealing with force and some equations dealing with frequency. So you don't want to confuse them. All right. Now, I've given you the definitions for period and frequency. Now, there is a way to calculate it. However, there is no equation provided on the reference table. So in this question, what I want you to try to do is use the definition I gave you to figure out how to calculate the period and frequency. So pause the video and work on yourself, and we'll go over in a second. All right. So the first question is, what is the period of the cycles? So if I go back to the definition of the period, it was the time it takes for one cycle. Time for one cycle. Time per cycle. That means I'm dividing time and cycles. So again, this equation, this quote unquote equation, comes from the definition that period is time per cycles. So I take the 5 seconds, divide it by 10, and I get 0.5 seconds. One thing to note, you'll notice that I didn't write 10 cycles back here. As far as physics concerns, when you're doing when there's a number that's representing like a counting thing, like, you know, the number of cycles, the number of beans, or the number of cars that you're dealing with, that doesn't need to be included as units. Units that they care about are SI units, you know, things like meters, kilograms, newtons, seconds, hertz. All these are considered real units. Cycles, oscillations, they can be dropped pretty much immediately. But if you want to put it in here, it would be 0.5 seconds per cycle. All right, so part B says, well, what's the frequency of the cycle? Again, I have to go back to the definition. The frequency was defined as the number of cycles per second. So again, using that same idea, the same way I did for period, frequency is number of cycles per seconds, per time. So cycles divided by time gets me frequency. Basically, I do 10 divided by 5 seconds time, and I get 2 hertz. So these are two equations that you have to end up remembering. Like I said, they come straight from the definition, and they do not appear on any equations. One thing that kind of makes it easy, because some people can forget like which one was time on top. I always just remind myself that, again, period is a unit of this time. So time should be top billing. It should be up top because, you know, that's where the period is. Frequency is not time. It's just the number. So time should be on the bottom. Time should be kind of, you know, secondary. One other thing that I want to point about frequency, I forgot to mention this, but you might, if you're part of music, you might actually have seen some frequency before because of different sounds. For example, 256 hertz is a typical C note. Basically, what this frequency means is that the sound produced by this note produces 256 cycles every second. So when the sound hits your eardrums, it's causing your eardrums to vibrate 256 times every second. And that's where the notes are coming from the oscillations in the eardrums and the oscillations in all the different items in the stuff. So just want to throw that out there. Now, if we look at the equations, period equals time over seconds, and frequency is cycles over seconds. So that leads us into this definition. Now, this actually is an equation given on the reference table. Why? Because it's actually extremely important. But basically, the big takeaway is that period and frequency are reciprocals of each other. That once you know one of these, you automatically know the other. So you know frequency, you automatically know period. And if you know period, you automatically know frequency. In fact, it's the only one that I can think of that has this type of relationship, and it is definitely used very frequently in this topic. So you definitely want to make sure that you remember this. Now, big question is, well, why is this important? Why would knowing that period and frequency are reciprocals? Well, the first one is to help bridge between the different equations. So, for example, you might find that you have an equation that calculates for period, but the equation that you do have to use uh, requires frequency. Well, in order to find that bridge, what you'd say is, okay, well, I can use this equation to find period, and then I take the reciprocal, and that gets me the frequency. Or if they give you the period and you're trying to you're trying to use an equation, and the only ones that you have are frequency, then you automatically know, oh yeah, that's right. Now that I have the period, I automatically know the frequency. So it really helps kind of open up more avenues essentially to other questions. Uh, Kind of similar to how acceleration was so important, bridging between kinematics equations and force. But the difference there was that in order to actually find the force, once you have an acceleration, you also needed mass. So if they didn't give you mass, you couldn't find the force. Here, that's not the case. Once you have one, you automatically know the other. But there actually is a second reason why this is important. Now, this plays more into regions questions that you'll see, but the AP will probably throw at least one curveball like this at you, so you want to kind of keep an eye out for. But basically, it's to limit multiple choice questions, multiple choices. So, what do I mean by that? Consider this question. As a wave travels into a different medium with a change in direction, there will also be a change in the wave's blank. Now, we don't know the answer to this. We haven't talked about wave traveling between mediums, and some of these terms you might not know. But right off the bat, if I was to guess right now, I'd have a 25% chance of getting it right because there's one correct answer and three wrong ones. But based off of this wording, I know that frequency and period have to be taken out of the equation because if there's a change in frequency, since frequency is the reciprocal of period, that means period also changes. If the frequency was originally 1 hertz, let's say, then the period was 1 second. If the frequency changes to 2 hertz, well, the period must also change to half a second. So if you have a question where it's asking like, oh, there will be a change in, or what will stay the same, and you have both frequency and period there, you know that they can't be choices because they automatically contradict each other. If the answer was, if you decided that frequency changed, well, that means period also has to change. So you have a contradiction, two correct choices. Now, the reason why I said that you might want to keep an eye out for this is because at the first point, AP does throw in some double question, some multi-correct choices. So you might actually see a question where there's two correct answers, and you just want to realize that if you realize that the answer to one was phase and you're kind of thinking about frequency, that frequency and period kind of get lumped together. To keep an eye out for that. Also, they could throw in stuff like that. The one thing that I do want to point out though is that if this was worded slightly differently, so let's say I instead said there will be a increase. I probably shouldn't have deleted what I wrote, but whatever. Let's say they said there will be an increase in the waves blank. Well, now they're actually frequency and period would actually be up for grabs. So as we saw here, going from 1 hertz to 2 hertz was an increase that resulted in a decrease in the period. So an increase in one wouldn't mean an increase in the other because they're reciprocals. So yeah, you do want to pay attention to what the phrasing is of the question, because it's only if they're being kind of vague about it, about whether it is or isn't changing. But if the scenario is like, how is it changing? Is it increasing or decreasing? Then you can't make that same claim that you did before. All right. And that's pretty much it for this. Oh yeah, so I wanted to say before that, based off of this, the original phrasing of change, since frequency and period are now out, I now end up having a 50-50 shot in deciding which one of these could be the correct answer. So that's pretty much it for a lot of this terminology. Like I said, we're probably going to be covering a lot more of this stuff as the unit goes on. It's actually a fairly short unit. I'm sure this video kind of went a little bit longer, but that's just because I went into a little bit of detail. But for the most part, if a lot of these things don't make sense right this second, there are going to be things that you'll constantly see throughout the problem. Like you'll constantly see the word equilibrium point and amplitude and period and frequency and oscillations and cycles. So eventually you'll start to kind of soak it in. But I just want to cover it right off the bat right now so that you at least have a little bit of foundation. All right, if you have any questions, feel free to let me know. Otherwise, good luck and have a great day.